Hey everybody, Dr. Retzik here with you. This is our third video in section 7b, where we finally get to prove the real spectral theorem. So we already know that for a complex inner product space, an operator is normal if and only if there exists an orthonormal basis of eigenvectors. This is not the case over a real inner product space, and we're trying to decide, well, what's the condition to replace normality with that is equivalent to having an orthonormal basis of eigenvectors? That condition is for T to be self-adjoint. Let's get started. Okay, so we're just going to jump right in. It's time. Let's state this theorem and let's work our way through the proof. Okay, so this is the real spectral theorem. Okay, so let's make sure we know the setting. Let's see, let capital V be a non-trivial, so it's more than just the zero vector, real finite dimensional inner product space. So we're pretty far down in there right now. This is a very, very specific setting in which the problem occurs. Okay. The conclusion is then T is self-adjoint. So remember, that just means T equals T star. If and only if big V has an orthonormal basis of eigenvectors of T. Okay, so this one is the cousin of the corresponding result for complex inner product space. Here, it's self-adjoint that characterizes the type of operator where you can expect an orthonormal basis of eigenvectors. Back in the complex spectral theorem, it was not self-adjoint. You could be a little looser than that. Normality was the ticket back there. Okay, let's prove this thing. Proof. All right, now let's keep our wits. It's a big if and only if. And the reverse direction is easier because in the reverse direction, you're making this giant assumption. So in the reverse direction, you suppose E1 through En is an orthonormal basis of eigenvectors of T. Okay, well, that's a pretty enormous supposition there. And if you have such a thing, then in particular, the matrix for T with respect to that basis is lambda 1, lambda 2 through lambda n, zeros everywhere else. They're eigenvectors after all. So T of E1 is lambda 1 E1 and T of E2 is lambda 2 E2. And so your matrix representation is diagonal already. And since this is happening over the real field, all the entries in that matrix are real numbers. They're real scalars. So in particular, the conjugate transpose is just the transpose, but the matrix is diagonal. So the transpose is identical. So the matrix for T star is the matrix for T. And that's it. So T must equal T star. They have the same matrix representation with respect to that basis. So that's it. So that direction is not the big deal, actually. The big deal is the forward direction. If you assume that T is self-adjoint, from that assumption alone, you can argue that there must be an orthonormal basis of eigenvectors of T. Okay, so let's start the forward direction. Okay, so let's keep clear. What are we doing here? We're supposing T is self-adjoint. Suppose T equals T star. That's it. That's all we got. Okay. We're going to proceed by induction on the dimension of V. This reminds me of our argument way back in 306 when we were proving that over a complex finite dimensional vector space, you definitely have an upper triangular matrix representation. We proved that by induction as well. And so this has like a similar structure, totally different words and little facts involved, but it's a similar structure. Okay, so let's see here. Let's proceed by induction on the dimension of the space V. So for a first order of business, let's prove that there is an orthonormal basis of eigenvectors of T in the event that V is one-dimensional. So step one. If V is equal to the span of little v, and then I guess parenthetically with little v not equal to 0, because big V, remember, is non-trivial. There's something non-zero in there. So if V is one-dimensional, meaning it's spanned by this one vector, little v, then little v divided by its own norm is an orthonormal basis of eigenvectors of T. Now, let's make sure we believe all that. Okay, orthonormal. Well, normal because this is a unit vector by design. So the one vector in this basis has norm 1, so that's good. Ortho, well, is that vector orthogonal to every other vector in the basis? And the answer is yeah, because there are no other vectors in the basis. So a one-dimensional vector space, bases are automatically orthogonal because there's only one thing in the basis. Now let's talk about eigenvectors. Well, apply T to that one vector in this basis. Well, you have to end up in V still. And since V is spanned by little v, you would just be some multiple of that vector. So indeed, in kind of the lamest possible way, if V is one-dimensional, then for sure the statement is true. Okay, and I don't think that even really has anything to do with T being self-adjoint. Okay, so now, step 2, we're going to assume the dimension of V is n. Assume dimension V equals n, bigger than 1, and that T self-adjoint implies ON basis of eigenvectors on any real inner product space of dimension less than n. Okay, so we're assuming that the forward direction of this proof, that implication is true on real inner product spaces of dimension less than n, and we're trying to argue that it's true on real inner product spaces of dimension n. So that's what we're trying to do. Okay, so here's the move. We got to start thinking geometrically a little bit. So here's the situation. So here's V. And we have our self-adjoint operator in this direction of the proof. In fact, that's all we know about T, is it's self-adjoint. So we know T star equals T, and that's it. Okay, and we know V's dimension V is n. Great. Okay, now, the technical groundwork that we've been doing here the last couple days in 7b comes into play right now. We know that since T is self-adjoint, T has an eigenvalue. So since T star equals T, there exists V in big V such that T acting on V equals lambda V. In other words, there is an eigenvalue with some corresponding eigenvector. That little v is non-zero, so maybe little v is here. And maybe this is the span. This one-dimensional thread right there is the span of V. So this is all possible multiples of that one V. So maybe like zeros right there. Okay. Let U equal that red one-dimensional span of that one vector. Let U equal the span of that one V. So that red strand right there running through our picture, that's a subspace U. Okay, now U perp in green must sit like this. There's U perp. Now we know from chapter 6 that V is equal to U perp. And in particular, once you know that V is equal to the direct sum of U plus U perp, direct sum of U plus U perp. Did I say V was equal to U perp? That's weird. No, it's the direct sum. That's how this always works in a chapter 6 way. And therefore, and thus, the dimension of U perp is n minus 1. Okay, so that green subspace U perp is dimension less than V's dimension. which means in this step of the induction proof, if we could argue that T was actually an operator on U perp and was self-adjoint still, then we would know that there was an orthonormal basis. Sorry, I'm trying to kill a bug. That there was an orthonormal basis of U consisting of eigenvectors for T. And then maybe that basis we can extend to an orthonormal basis for the entire box V. Okay, so it's down to making this argument. Is it true that U perp is invariant for T? In other words, is T also a perfectly good operator just on the green blob rather than on the entire box V? And here you got to recollect weekly, it was Axler 7a, problem 3 on the weekly homework you guys just turned in, which said, at the time it said, if U is a subspace invariant for T, then U perp is a subspace invariant for T star, and vice versa. It was an if and only if. But in this problem, T is T star. So I'm just going to say it like this. Oops. Let's go with the black ink. By 7.A.3, T, which is T star, does map U perp into U perp and is, of course, still self-adjoint. If you restrict that self-adjoint operator to an invariant subspace, it's still self-adjoint. Self-adjointness that's a thing about the inner products and flipping T from the first slot to the second slot. That has nothing to do with whether you're in the green blob or not. That's just true in the entire box. So by induction, there does exist an orthonormal basis. Got it. ON basis E1 through, okay, how many things should be in that basis for U perp? E1 through En minus 1? For U perp consisting of eigenvectors of T. Fantastic. Now, but we were trying to argue that there was a basis for all of V that was orthonormal and consisting of eigenvectors of T. But we win now. So original little v divided by its own norm, just to make it length 1, attached to the E1 through En minus 1 we just granted ourselves from U perp is an ON basis for V consisting of eigenvectors of T. And that's it. So the gist is this. In the forward direction where you assume T is self-adjoint, you have that earlier groundwork that says, look, I don't know about a full-on basis or whatever, but there's definitely at least one eigenvalue-eigenvector pair. Name that eigenvector. Use it to span a one-dimensional subspace U. Generate the perp to that one-dimensional subspace U, call it U perp. U perp is of dimension 1 less than the dimension of V. And therefore, by our induction hypothesis, we can gather up an orthonormal basis for U perp consisting of eigenvectors of T. To that, we can attach the original vector V divided by its own length. And now you have an orthonormal basis for the entire box. I mean, after all, there's n things in it, and they're linearly independent because E1 through En minus 1 already are, and V is perpendicular to all of those, so it can't be a linear combination of them. V comes from U, the rest of them come from U perp, so the whole list is orthonormal. And that's it. Okay, so zoom out. Basically what you got going here is this. When F is equal to C, then in this box of all linear operators on V, the nice ones are the normals, where the definition of the word nice in that sentence is they have a diagonal matrix representation with respect to an orthonormal basis of eigenvectors. When F is equal to R, and you're looking at all possible linear operators on V, well, you got to do a little better than normal. You got to do self-adjoint. Sorry, now there's the dog. The self-adjoints are the ones that are nice, where the word nice means have a diagonal matrix representation with respect to an orthonormal basis of eigenvectors. Now, that means down in this box, the normals are not nice enough. So the normals sit like this in this big box of linear operators on V. And the question becomes, okay, wait, so the normals aren't that nice. So if you're merely normal and not self-adjoint, there's no expectation that you have a diagonal matrix representation with respect to an orthonormal basis of eigenvectors. Okay, well, what do you have? I mean, normal seems pretty nice. You must have something, and actually, it's pretty close. There's an orthonormal basis of eigenvectors such that the matrix for your normal operator is dang near diagonal. Dang near. Not quite, though. Anyway, that's a discussion for a different time. For us, nice when F is R means self-adjoint. Nice when F is C means normal. All right, we got it. The spectral theorems are in the books. See you next time.